Alright, here we're going to add or subtract radical expressions where we first need to simplify the radicals to figure out if we have any like radicals that can be combined in the first place. So let's start with square root of 5 plus square root of 20. Right now they're not like radicals because like radicals have to have the same index or the same root type, so they're both square roots, but it also has to have the same radicand, which means the insides of the root, and these two have different insides. So first thing we're going to do is simplify root 20, and then we'll see what we're left with after that. Now 20 is 4 times 5, so I'm going to rewrite root 20 as, so I just bring down the root 5 plus, and rewrite this as root 4 times 5. And then we can break it off and say root 5 plus, and we can split root 4 times 5 into root 4 times root 5. And that means we can go ahead and take the root of 4. Square root of 4 is 2. So now we have root 5 plus 2 root 5. And now looking at it, we have like radicals because we have square root 5, square root 5. Now we can combine their coefficients. And remember, if you don't see a coefficient, that means it's a 1, even though it's not shown. Combining the coefficients, we have 1 plus 2, root 5, or 3 root 5. Now I left a gap there on purpose because there's a certain way I want you to think about combining the coefficients that'll make it a little bit easier to understand this next problem that we're going to do. Think about it this way. We have root 5 and root 5 in common here, so we're going to factor it out. So if we factor out the common root 5, what we're left with, or undistribute it, we're left with 1 plus 2. So that's really what you're doing when you combine like terms or like radicals, is you're undistributing the like part, and what you're left with is combining the coefficients in the front. So we have 1 plus 2 is 3 root 5. Okay, now for this problem we didn't have to do that step, but on this problem we are going to have to do that step. So let's see how that works. Right now we don't have like radicals because even though they're both square roots, the insides are different. So what we want to do first is simplify this guy and see what we get. So we want to break down 32 and x cubed into factors that contain perfect squares. So 32 is the same as, and let's go off to the side here for that. For 32, we could have 2 times 16, 8 times 4, and 4 is a perfect square, and so 16. And I'm going to use 2 times 16 because I want to use the highest possible square root. So I'll rewrite this as 16 times 2. And then for x cubed, the highest possible square that I could break that into is x squared times x to the 1, where x squared is a perfect square. So 16 and x squared are perfect squares. And I'll just bring down the plus root 2. There's nothing we can do with that, or root 2x. And now we keep going with this guy. We're going to break it up and say first the perfect squares, square root of 16x squared, times the not perfect squares. So that'd be times root 2x. And bring down this other root 2x. And now we can look at it and see that we have like radicals. Square root 2x, square root 2x. And again, this has a 1 in front of it, even though nothing's shown. So we can go ahead and take the square root of 16x squared, which is 4x, and times root 2x stays where it is, plus 1 root 2x. And now we can go ahead and combine the like radicals. And here's where we're forced to use that step that I showed over here, where we undistribute the like radical. Because now we can't combine 4x plus 1 any more than just saying it's 4x plus 1. So I'm going to put parentheses, undistribute the root 2x, and then 4x plus 1 are the leftovers. So that's combining the coefficients right there. And there's nothing else we can do to it. And that would be our answer. What you want to be careful of here is not to put the answer without parentheses, because if I said 4x plus 1 root 2x, then this 4x is not being multiplied by the root 2x, but it has to be. So I want the parentheses around the 4x plus 1. And the last one. Same idea, except now we have cube roots. So we just want to be really careful when we're simplifying the radicals to break into factors that are perfect cubes, not perfect squares. So let's see. First we'll start off with 24xy cubed. Now y cubed is already a perfect cube. So any exponent that is divisible by the index of the root would be a perfect root. So I need to break 24 now into a perfect cube. So 24, if I list some factors, I have 2 times 12, 3 times 8, 4 times 6. 8 is a perfect cube. So I'm going to use 3 times 8 to break that into. So I have cube root of 3 times 8 times, and then I'll just bring these guys down. X times y cubed minus y cube root of, and for 81, we can break that up. Now 81 is 9 times 9, and 9 times 9, well, that would be 3 times 3 times 3 times 3, and sometimes writing it out like that completely factored can help you find where the perfect cube is. So if I have 3 of any number multiplied by itself, that's going to be a perfect cube. So 27 times 3 is what I want to use inside my root, because I know that 27 is a perfect cube. So 27 times 3, and then bring down the x. And now we'll break it into perfect cubes and non-perfect cubes in both of these radicals. So for the first one we have cube root of 8y cubed for the perfect cubes times the non-perfect cubes are 3x, so cube root 3x, minus y times cube root, the perfect cube is 27, times cube root of the non-perfect, which is 3x. Now we'll go ahead and do the perfect cubes. So the cube root of 8y cubed gives us 2y, and we still have times cube root of 3x. And here we have minus y times the cube root of 27 is 3, so that gives us minus 3y, so 3 times y. Bring down the times cube root of 3x. And now we check to see, do we have like radicals? Cube root 3x, cube root 3x. Yeah, those are like radicals. We can combine the coefficients. 2y minus 3y is negative 1y, or just negative y. And write the like radical next to it, and we have our answer.